Hi, everyone. Today we're going to be talking about free fall and gravity uh, and how objects are affected in free fall. So, you saw from the simulation that all objects in free fall are only acted upon by just one force. That force is gravity. Now, gravity is going to pull things towards the center of the earth at a specific rate, which we'll talk about later. Gravity is essentially a attractive force between two objects. These objects need to have some sort of mass attached to them. So even between you and I right now, there's a gravitational attractive force that's kind of calculated between how far we are apart and how heavy we are. The heavier you are, the more attractive force you have between two objects. You've kind of seen this in your breakfast cereal every morning. Uh, if you take two Cheerios and put them on top of milk, you'll see the surface tension actually pulls the two Cheerios together over time, no matter how far away they are in the cereal bowl itself. So those two Cheerios will have some attractive force because they have mass, and then they have a distance between them. The closer they get, the less obviously distance between them you're going to see. This can be at a massive level too, right? The Earth, which is I'm drawing here, it's a sad Earth, um, is is keeping the moon in orbit because there's a gravitational force between the moon and the Earth. This is a result of the distance between it and the size. Obviously, the Earth has a way more gravitational pull than the Cheerios. Now, if we were to take like a a magnifying glass, and zoom right in on the Earth and the moon, you're going to see that this gravitational field acts the same no matter where you are on Earth. So if I was Isaac Newton back in England thinking, hey, this apple is going to fall down, I can calculate that this apple is always going to accelerate at negative 9.8 meters per second squared on Earth. So no matter where you are, whether you're at the North Pole or the equator or the South Pole, all objects on Earth are going to accelerate at 9.81 meters per second squared. And so acceleration, we kind of talked about, is that it's kind of like your meters per second, which is your speed, increasing over time. So when an object is accelerating at 9.81 meters per second down, every second that passes is going to be gaining 9.81 meters per second of speed. Now, this doesn't always happen because sometimes objects are going to reach what we call terminal velocity. Now, terminal velocity is when an object reaches its maximum speed. Uh, and if you think of that, uh, when you drop two objects, you want to believe that they're going to fall at the same rate, but they will not because your terminal velocity changes based on the properties of the material you're dropping, right? Which would you rather get hit by? A piece of tissue paper from the CN Tower or a bowling ball? Obviously, you're going to pick a piece of tissue paper. That's because they change, their terminal velocity of that object is different depending on the material. Usually, the terminal velocity is reached when the frictional force is equal to the gravitational force. So let's just say a piece of paper. What if I crumple up a piece of paper and drop it versus a piece of paper that hasn't been crumpled up at all? Which one do you think will hit terminal velocity first? Clearly, the unfolded piece of paper is going to hit its terminal velocity first because you know it's going to hit the ground second because the air resistance is much bigger on an open piece of paper rather than a crumpled up ball. So the crumpled paper is slower to reach terminal velocity because it's going to accelerate at 9.81 faster before it reaches its terminal velocity, which is kind of confusing. So if you reach your terminal velocity fastest, you're going to be falling slower. And vice versa. If you're really slow to reach your maximum speed, you're going to be falling faster. I got a little bit ahead of myself here. So the non-folded will be reaching it faster. So there is a whole bunch of cool videos on the internet talking about terminal velocity, which I'll post underneath the link. Now, terminal velocity, there are situations we can set it up where there is no air resistance in a system. We call that a vacuum. Usually these vacuums don't exist, but we kind of pretend in physics that they do. And so in a vacuum, there is no air resistance. And everything is going to fall at the exact same rate, which means that both a crumpled up piece of paper and an uncrumpled piece of paper will have the same terminal velocity, and it will continue accelerating downwards, which is pretty cool. So what you'll see in this next video by Brian Cox from the BBC, he is going to drop in a massive air chamber a bowling ball and a feather. And you will find that in a vacuum, that both the bowling ball and the feathers drop at the exact same rate. And that rate is negative 9.81 meters per second.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side. I'll let the
Exactly the
closer
same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.